And 114. So for anyone, is anyone else on the wait list before everyone else is in like Flynn? Okay, good. Just keep coming to class and hopefully it'll sort itself out. Great. Okay. Feels like forever ago that we met. I guess it was just on Wednesday, but let's do just a quick review because we're moving on to new things today, but just to summarize what we did. So we talked about dealing with fractions. Remember in chapter 1, we're just laying out all the basics that I need you to know for the rest of the course, right? So how do we deal with fractions? What's the order of operations, right? So what's bed mass, that kind of thing. And so that's why chapter 1 seems like, oh, okay, it's a lot of, pretty basic stuff, but it's just so we're all on the same page, right? And if you're having a hard time with it, then definitely make sure that you review all these things because I need you to know them, okay? So as far as the review goes, we talked about fractions and we talked about expanding and factoring. Let me just make sure I'm recording. Yeah. So fractions, we talked about how do we add, subtract, multiply, and divide fractions, right? So we went through all of those together. Okay. And if you weren't here last class, then you can watch the video from last class. Remember, so on Moodle, I've posted the link to all the YouTube videos. So you can, if you miss a class, then you can go back and you can watch the video. It even can add subtitles, and then it's easy to hear what I'm saying. Or it'll try to add subtitles. I'll try to keep it on its toes. And then we talked about expanding and factoring. Right. Expanding is just when we get rid of all these brackets, and then factoring is where we kind of suck everything back together, right? So kind of make it as condensed as it can be, right? Pulling out common multiples, putting brackets around stuff, right? So we talked about expanding and factoring. And so that's about, seems like not very much, but it's actually quite a bit to talk about, right? But that's what we talked about last day. And so any questions about that before we keep going? Oh, no questions from last day. So I did tell you guys to work through some problems. I don't want you to hand those in, right? But those are just for you to make sure that, okay, I know what I'm doing here, right? I feel comfortable moving forward. And if there are things that are coming up and you're having troubles with, then you should come talk to me about it, right? And we'll figure out what's going on, okay? So we're gonna finish chapter 1 today. Okay? So 1.5 is on solving systems of equations. So solving systems of equations. Solving equations is kind of basically all we'll be doing in this class, right? So we'll be given some equations and you have to solve them one way or another. And so solving a system of equations is kind of the basic way to do that. Okay. So first, let's look at what a system of equations looks like, and then we'll talk about how do we solve it. So a system of equations looks like, maybe we have 4x plus 2y equals 8. And then below it, we have another equation, 2x minus y equals 7. So here we have two equations. An equation is anything with an equal sign in it. Right? And so here we have two equations making a system. Right? And what we're saying here is we have to find an x and a y that makes both of these true. Then we've solved the system of equations. Okay? So to solve a system of equations, we need to find one x and one y, right, at the same time that'll solve both of these equations. We need to find, I'll say, the combination of x and y that solves both of these equations. That solves both of these equations. Here, right, we've got an x and a y in each of these equations, right? So we have two unknowns. And so to solve for two unknowns, we have to have at least two equations. So you have to have as many equations as you have unknowns. Okay? So here, these are unknowns, the x and the y. Okay. And two equations needed to solve for two unknowns. Try to squeeze that in there. Unknowns. I kinked my neck this weekend, so I'm kind of like, ugh, can't move. Anyways. So of course, if you have three unknowns, x, y, z, you would have to have at least three equations. That's just a little side note. So to solve a system, or I guess just good to know stuff. So to solve a system with three unknowns, we would need at least three independent equations We'll talk more about independence later. Okay. So you might recognize the equation of a line, right? Y equals mx plus b or something like it, right? So a line has two unknowns, an x and a y, right? And so both of these equations that we have here make straight lines. So we'll only deal with straight line equations, right? And so in general, a straight line has the form y equals mx plus b. Right. Where x and y are unknowns. Right. If you have these equations that we were looking at, could you solve for y and get it into the form of y equals mx plus b? Absolutely, right? you could rearrange each of these equations and get it into y equals mx plus b, right? So as soon as there is just one x and a y equals something, you have a straight line, right? So we can rewrite we won't, but we could rewrite 4x plus 2y equals 8 right, as what? 2y equals 8 minus 4x. This is where our math manipulation skills come in handy, right? Solving for y, we get y equals 8 minus 4x over 2. 8's divided by 2, so y equals 4 minus 2x. Right? It's not something that we have to do, but I'm just showing you that we could, if we wanted to, we can manipulate these. As long as there is an x and a y, we can get them into this straight line form. Okay. And the reason that I'm leading you down that path is because to visualize solving a system of equations, right, we're going to have something like this, right? So we're going to have a grid of some sort. So we've got x, we've got y, and let's say we've got equation 1 here and equation 2 here. So equation 1, equation number 2. This is just in general. This isn't referring to the ones that I gave you, right? It's just to visualize that at this point, right, at this point where they intersect, we've got an x coordinate and a y coordinate. And at that single point, we've solved both systems, right? Because that point is true on this line, but it's also true on this line, right? And so at the same time, this xy coordinate solves both equations at the same time. So the point of intersection, here I'll draw a little arrow here. The point of intersection is the solution to the system. So that's what we'll be doing in the background. We won't necessarily be drawing these things and figuring out where they intersect, but if we did, it would look like that, right? Where they cross, the point where they intersect, that's your solution. So we need to find x and y that satisfy both equations at the same time. That satisfy both equations at the same time. So that's the goal. Now, there are two common methods for solving systems of equations. I have a favorite, and so that's the one that I'm going to stick to. I'll talk about the other way, and the textbook goes through and shows you how to do it. I find my way is a little bit more trustworthy because it's easier to make mistakes with the other way. So, but it can be quicker. Oh, that's big. Here, there are two common methods for solving systems of equations. So there are two common methods for solving systems of equations. Systems of equations. First one is by substitution. Okay? So just you look at these, and I'll write it out in words, but it's going to make more sense once we do it. Okay? So what we would do is we would say, okay, here's my equation 1, here's my equation 2. Let's say game changer or something. No, got a little notification. Anyways, if you're trying to chat with me, try again. Sometimes I'm not too good at using Zoom yet. So if you're on Zoom and trying to ask a question, I'll probably miss it. So that's why I'm saying ask again. But what we're going to do is we're going to call this equation 1 and this equation 2. That seems reasonable, right? And then what we're going to do is we're going to solve for one of these variables, whichever one is easiest to solve for, right? Here, I think solving for y in equation 2 looks pretty easy, right? I can shake out y and get y on its own. That seems doable, right? I can move this 2x over here and then move the negative over. And then I have y equals whatever, right? Then, because I got that from equation 2, I need to plug that y into equation 1. That means I've gotten rid of all my y's, and now I only have x's, right? So that'll let me solve for x, and then I can plug that in and solve for y. So what I'm doing, right, is I'm solving for this, and then I'm substituting it into here, and that's why this method is called solving by substitution. And even though it sounds tricky, it's the easiest method, I think. So that's the one that I'll use. Let's write this one out, and then we can talk about the other method, which is by elimination, and the textbook goes through it in detail. But like I said, I like to just have one method for solving things, right? And then if you want another one, it's there. So first method is by substitution. Solve for a variable. So I'm not going to tell you which one, just whichever one is easiest. Solve for a variable in either of the two equations. In either of the two equations. Then substitute, hence the name, by substitution, then substitute that answer into the other equation. Then substitute the result into the other variable, or sorry, into the other equation. Now you can solve for the other variable, right? So the one that you didn't solve for initially, now you can actually find a value for it, right? So solve for the other variable. And then use the solution to solve for the first variable. wordy, but I'll show you by example. So for the other, use the solution to solve for the first variable. We'll just talk about the other method, which is by elimination. So the second method is by elimination. And just going back to our little example here, there. If we had to solve this by elimination, what we would do is we would multiply either of these by some number. So any number that you want, right? As long as you do it all the way through. So for example, I might multiply this equation by 2, right, entirely. And then to try to eliminate the x's, I would subtract this equation from this equation, right? I would take this equation minus 2 times this equation, which gets a little tricky because whenever I try to do it, I always forget to deal with these ones, right? But if you're multiplying this equation by 2, right, you get 4x minus 2y equals 14. And that's the one I always forget. That's why I like the other method. But then, now that you have 4x minus 2y equals 14, to try to eliminate your x's, right, that's why we multiplied by 2 to get it to be the same as the 4x. You can do equation 1 minus 2 times equation 2. Right? So then you would have 4x minus 4x is 0. So now you've eliminated those x's, right? And now you have 2y minus 2y, not very helpful, right? But then we get to, nope, not 2y minus. This is why it messes me up, because I forget I'm minusing a minus. 2y minus negative 2y makes 4y. Messes me up every time. If it's not this side, it's this side. Okay? But if it is something, so you can see that it can be a little bit cleaner than by substitution, a little bit faster. So if it is something that you like, right, then you would end up with 4y equals 8 minus 14. Right? And then you can solve for y, and then you can go back and figure out what x is. So if it is something that you like, then absolutely go ahead and use it. But I'll just do substitution. Okay? For obvious reasons. I messed up potentially twice if I forgot to pull through to the other side of the equals. But here in words is what we're doing. So take a multiple of one equation and add or subtract it to the other equation in order to eliminate one of the variables. And so the whole goal is to try to eliminate one of these variables. And add or subtract it to the other equation in order to eliminate one of the variables. Now you'll be left with one variable that you can solve for, right? And then you can use that to solve for the other variable. So now you will be left with one variable which you can solve for. Then use that solution to solve for the other variable. Then use that solution to solve for the other variable. Just make a note here that I prefer to solve just by substitution, right? It's a little bit longer, but like I said, it's a little bit safer, for me at least, because I skip steps and mess up. So I prefer solving by substitution. I prefer solving by substitution. So that's the only method that I'll use, right? Of course, you're welcome to use elimination if you prefer. So that is the only method I will use. The textbook covers solving by elimination. The textbook covers solving by elimination. So there are methods in words. Let's have a look at this example here. So if I had to solve, and I'm going to use the same equation that we just had, 4x plus 2y equals 8, and 2x minus y equals 7. So definitely on test 1, I'll make you do this, right, where you have to solve systems of equations. And so the first thing that I'm going to do is I'm just going to number these 1 and 2 just to make it easier to refer to them, right? So I'll just put a little 1 and 2 here. And then as I go, I'll make little notes to myself what I'm doing, right? Try to make it clear. So looking at this, I'm still thinking that solving for y in equation 2 looks like the easiest thing to do, right? Because it's not attached to anything. It's just got that negative there, which we can deal with, right? But we can solve for any one of these, right? So we can use the first equation with the 4x. We could, if we wanted to, solve for x. But with a little bit of foresight, we could say, well, that's going to get us 8 minus 2y, and then we have to divide that by 4. 2 divided by 4 gets a little nasty. I don't like to deal with fractions, so I'm going to avoid it, right? And so the easiest way to kind of avoid that is to go for the simplest variable. So again, doesn't matter which way you do it, you'll get to the same answer. So I will solve for y in equation 2. So now I'm focusing on equation 2. Equation 2, right, is 2x minus y equals 7. and I'm going to solve for y here. So I need to move the 2x over, so I need to subtract 2x from both sides, so I get negative y is 7 minus 2x. And then I've got the negative y, so I need to move that negative over, and even though we're technically dividing by -1, I just multiply it by -1. That gets rid of it too. So then we get y is negative 7 minus 2x. Careful with those brackets. If you ditch the brackets right away, then you would have to have negative 7 plus 2x, right? So now we have y equals negative 7 plus 2x once we expand those brackets out. So now we know that y is negative 7 plus 2x. Whatever x is, that's going to be our y. Okay. So now, remember, we got this y out of equation 2. So putting it back into equation 2 is just going to get you to loop back through. It doesn't get you anywhere further, right? So now you're going to take this y and put it into equation 1, right? You're going to substitute it into equation 1. So next step I'm going to do is I'm going to substitute y equals negative 7 plus 2x into equation 1. Whatever equation you didn't get it from. So equation 1, let's copy it out, 4x plus 2y equals 8. 4x plus 2y equals 8. That's equation 1. So now, right, I've got my 4x, that's not changing, but I'm going to change my y and replace it with negative 7 plus 2x. Right, so I'm going to substitute it in. So I get 4x plus 2 times y, which is being replaced by negative 7 plus 2x equals 8. So now in our equation, we've reduced it, so we just have x's in here, right, which we'll be able to solve for, right? We'll be able to solve for x. So here, right, we can expand and then simplify, right, collect like terms like we've been doing in the previous sections, right? So it's all kind of getting applied now. So we get 4x, and then plus 2 times negative 7 puts you at minus 14, right? And then plus 2 times 2x plus 4x equals 8. So you want to be careful with those brackets. Here, right, we've got 4x and then plus 4x, so we can collect like terms to simplify this. So we get 8x minus 14 equals 8. Right? 4x plus 4x is 8x. The negative 14 just stays negative 14. Looking good. Any questions so far? Okay, great. So now we're going to keep solving this equation for x, right? Because we just have that one x in there. And so we can solve for this. So we're going to move the 14 over. So we get 8x is 8 plus 14. So we have 8x is 22. So x is 22 divided by 8, right? Divide both sides by 8. And we find that x is 2.75. So now we know that x has to be 2.75. But we also found earlier, right, that y is -7 plus 2x, whatever x is. Now we know x, so now we can substitute it back in here, or any other of the equations that we were given. Right? They should all be true if this is a solution. So now we're going to use x equals 2.75 to solve for y. And you're going to recall that y was -7 plus 2x. That's the easiest way to do it, is to put it back into, or substitute it into, whichever one you found earlier. Or if you wanted to put it into one of those original equations, that works too. So now we have y equals -7 plus 2 times 2.75. Y is -7 plus 5.5. So y is -1.5. So therefore, the system has a solution at x equals 2.75 and y equals -1.5. So therefore, are you guys okay with therefore? Just 3 triangular dots? Okay. Therefore, the solution to the system is x equals 2.75 and y equals -1.5. What's nice about solving systems of equations is that we can check our work, right? Because we're saying that when x is 2.75 and y is -1.5, both of those equations have to be true, right? So when we plug those in, first one has to equal 8, the second one has to equal 7. If they don't, we did something wrong, right? Then it's not a solution. So I'll just make a note here. It's always a good idea to check your solution. So it's always a good idea to check your solution. So remember, equation 1 was 4x plus 2y equal to 8. So what I want to know is, when I plug in this x and y, does it equal 8? So I'm going to put a little question mark above the equal sign, right? Because I'm just making sure that that's true. So I've got 4 times x, which is 2.75, plus 2 times -1.5. Does it equal 8? I get 11 plus -3 does equal 8. So that's true. Yeah. How about the second equation, right? To be a solution, it has to solve both equations at the same time. So let's check the second equation as well. 2x minus y, does it equal 7? So we've got 2 times 2.75 minus -1.5. We're still not sure if it equals 7, so I'll keep that question mark up top. So we got 5.5 plus 1.5 which is 7. Phew. So these two lines intersect when x is 2.75 and y is negative 1.5. So in terms of just kind of taking it to a graph here, x, y, x is 2.75 and y is negative 1.5. This is where both of these lines intersect. So just imagine we've had, I don't know what these lines look like. Say this is equation 1 and this is equation 2. Something like that. Cool. Nice. Any questions about that one? So that's a big concept that we'll come back to, right? Solving systems and just solving equations in general, right? And I'll always come back to just doing it by substitution because I like to be methodical about stuff. So I like to solve for one variable, plug it into the next one, solve for one variable, plug it into the other one, right? It's kind of this back and forth game. So let's do another example. So example 28 from the textbook just says solve 2x plus y equals 4 and x plus 1/2 y equals 2. Now we got fractions in there. Luckily, we know how to add and subtract and manipulate fractions from last day. It's almost like it was planned. Almost. So I'll just give you just a quick second to get started on it. But not too long because it's a trick question. What? So here, I'll start by calling this equation 1 and this equation 2. Just the same way that we did just now. I'm going to look for something that's easy to solve for, right? So I think, because I don't like fractions, that's just me, I'll solve for y in equation 1. How about? I'll have to deal with that fraction one way or another, but I will solve for y in equation 1. So equation 1, right, is 2x plus y equals 4. So y is 4 minus 2x. All right. That was easy. So now we can substitute y equals 4 minus 2x into equation 2. Right? We took it from 1, so we put it into 2. So now substitute y equals 4 minus 2x into equation 2. And just a reminder, equation 2 is x plus 1/2 y equals 2. So now we have x plus, I'll make my fraction big, 1/2 y, and y we're substituting in 4 minus 2x, and then equals 2. So I do have to bring in this 1/2 inside the brackets, right? But both of them are divisible by 2, so it's not really a big deal, right? 4 divided by 2 is just 2, and then 2 divided by 2 is just 1. So now we have x plus 4 divided by 2 minus 2x divided by 2 equals 2. So we have x plus 2 minus x is 2. I told you it would be a trick question. I'm just trying to show you two scenarios where something like this might happen, right? Where we get to, I'll call it the end, right? Because now you're looking at this and saying, well, x minus x. So now what? Now I'm left with 2 equals 2. That's true. It tells us nothing about x or y, right? So it's not very helpful, okay? But what this is telling us is it actually doesn't matter what x and y are. 2 will always equal 2. I think we can all agree on that, right? And so that means that we have an infinite number of solutions. You can put in any x and y, and it'll still be a solution, right? And so because 2 will always equal 2, it doesn't care what x or y are. Okay, so this is a special case where we get to the end and we have this true statement, right, that tells us nothing about x or y. And that's telling us that we have an infinite number of solutions. Right? You can plug in any value of x and y and it'll be a solution. Okay? I'll make a note about that, but first I'll talk about the other option, a little bit worse. Right? What if you got to here and it said 4 equals 2? That's never true, right? So when you get to a false statement, right, that doesn't involve an x or a y, then you have no solutions, right? So those are those special cases where you either have an infinite number of solutions or no solutions, right? Or just like we did previously, where you actually have a solution, right? So most common is going to be, okay, there is a solution, I need you to find it, right? Or I also expect you to know how to deal with, okay, well, what does this mean? Right? Infinite solutions. If you come to a false statement, you have no solutions. So, as 2 equals 2 is true, or I'll say is a true statement, that doesn't specify what x is, right? So it doesn't care what x and y are. A true statement that doesn't specify what x is, we have an infinite number of solutions. We have an infinite number of solutions. Right? Any combination of x and y will give a solution. Right? That's what that's saying. Any combination of x and y will be a solution. So like I said, in a similar scenario, right, where you get to, I'm calling it the end, right, you hit a roadblock, 4 equals 2, for example, right, and you hit this false statement, that's telling you that you have no solutions, right, because it doesn't matter what x and y are, 4 is never going to be equal to 2. So in a similar scenario, if you get, I'll put in quotes to the end, right? Hopefully you understand what I mean by that, right? You do your calculations as you would normally, and then you hit a roadblock, right? Just like we did. So I'll say to the end. And find a false statement like 4 equals 2. There are no, so then I'll say then there are no solutions to the system. Meaning, right, going back to kind of the same drop down point as before, right? No combination of X and Y is going to yield a solution. No combination of X and Y will be a solution. So like I said, most often you'll be able to find a solution, right? But I need you to be able to deal with these scenarios, right? Where you get to the end and you just have a true statement versus a false statement. Any questions about that? No? Okay. Yeah, sorry.
Suppose if we use the elimination method, would we get the same answer?
Yeah, you will. You would, so if you use the elimination here, let's go back to here. Let's say you multiply this by 2, so just trying it by elimination, right? Multiply this by 2 and then subtract 1 from the other. So then you would have 2x minus 2x. So now your x's are gone, that's good. But then you have y minus 2 divided by 2y. So now you have y minus y. So now the y's are gone as well. Right. So now you've got, and then 4 minus 2 times 2 is 0. 0 equals 0. That's a true statement, but again, infinite solutions. So it's going to look a little bit different, right? We don't end up at 2 equals 2, we end up at 0 equals 0. But yeah, so you'll end up at the same thing with elimination as substitution. Any other questions? No, none. Okay. So, 1.6 is on ratios, proportions, and percentages. We're pretty familiar with percentages, especially you guys in business, right? So we know percentages, probably proportions as well, right? So again, chapter 1, we're just kind of getting everyone on the same page, right? Learning the lingo. In general, if we're using percentages, right, then we need to use the decimal form in our calculations. There are just, I think, 2 exceptions that I can think of, okay? But otherwise, we always just use the decimal version, right, which is a proportion. So a proportion times 100% is a percentage. Right, so a proportion is the decimal version of a percentage. So proportion is, I'll say, the decimal version of a, of a percentage. And so in our calculations, we should always use the proportion, right? Not the percentage. So in our calculations, we will use proportions, right? I'll put in brackets, not percentages. So 80% we would use 0.8 instead. 0.8 in calculations. So a proportion, right, is the decimal version of a percentage. So it makes sense that a proportion goes and is a decimal between 0 and 1, right? 0 to 100%. So a proportion is, it is a fraction, right? We usually don't write them as fractions, right? We use them as decimals. So often written in, written in decimal form. And takes on values between 0 and 1. Between 0 and 100%. So that's just some terminology and just kind of the ins and outs. Let's have a look at, I stole this. I've just taken a picture from the textbook, so I'll just copy it over. It's not a numbered example, but it's the peanut butter example, which I think is pretty funny. So it goes through and it has this big elaborate description of, so suppose that there are 2 goods required to make a good sandwich. Maybe a tasty sandwich instead. Peanut butter and bread. I'd argue for jam. We know that it takes 4 spoonfuls of peanut butter to cover 3 slices of bread. Right, so now we've got this ratio of peanut butter to bread. Okay. So the ratio of peanut butter to bread is 4 to 3. Suppose that we have 75 slices of bread. Okay, yikes, it's a lot of sandwiches. How many spoonfuls of peanut butter do we need to make sandwiches out of those 75 slices of bread? Right. So you know the ratio is 4 spoonfuls per 3 slices. Now you have 75 slices. How many spoonfuls of peanut butter are you going to need? And so suppose that X and Y represent quantities of peanut butter and bread respectively. And so, and then I've cut it off because here, I actually don't want you to get disheartened if you don't do it the way that I do. If we arrive at the same answer, you did it. There's lots of ways that we can think about this problem and lay out this problem, right? So I don't want you to get hinged on how I do it, right? This is how my brain works, okay? Your approach might be different, but again, if we get to the same answer, you did it. Okay? So, how I like to outline it is PM. I've got some amount of peanut butter to some amount of bread. You can do them as ratios like this, but I like to look at them as fractions, right? For every 3 slices of bread, I need 4 spoonfuls of peanut butter, right? So this I can write as 4/3. Just keeping in mind that the top value is the number of spoonfuls and the bottom value is the number of slices of bread. So now, this has to be equivalent to, right, this ratio or this proportion has to be the same for 75 slices of bread. So now I'm going to change this to 75 slices, right? Keeping in mind that they have to be the same across. And then I'm solving for how many spoonfuls it takes. So I'm just going to have X here and solve for X. And so how am I going to solve for X? Well, I'm going to multiply both sides by 75. You can ignore this chunk for now, right? I had that in the beginning to remind myself of how I'm setting this up, but now I can ignore it and just focus on these two, right? Solving for X, I can just multiply both sides by 75, and I can have 4/3 times 75 equals X. And it turns out that I would need 100 spoonfuls. Spoonfuls only has one L, I guess. Makes sense, but weird. Right. So if you got to 100, right, however in your mind you worked with those ratios and proportions, that's good. Right. And that's why I don't want to spend too much time on this section either, because we've already developed ways of solving these problems in our heads. Right? And so a lot of us kind of look at this problem, and however you want to work it out is fine. I won't be working too much with ratios and proportions anyways. Well, proportions, but ratios, nah. So let's have a look at something more important. Example 52. And like I said, I've just taken pictures of the textbook. So if you have the textbook and you want to follow along, that works too. It's a little small, but I'll read it to you. Last time I ate out, my bill was $45 before 7% tax and a 15% tip, okay, on the bill after tax. So that's saying, okay, so first you've got your bill, $45, and then you're going to pay 7% in tax. And then on top of all that, you're going to pay your 15% tip. Okay. How much did my night out cost? And so, all right, we've got some different components, right? We've got the original cost before everything, right? So the cost, so let's just outline what we're given here. Costs before tax and tip is $45. So cost, I'll say before the tip is $45 plus 7% tax. Kind of looks weird, but it is just the cost before the tip is $45 plus the tax. Right? So let's start there. So we've got, because we can solve for that, right? The cost plus the tip, or the cost plus the tax, sorry. So the cost before tip is $45 plus 7% tax. We're paying 7% tax on the $45, right? So how we find that is we say, bless you, 45 plus $45 times 7%. But remember, we don't use the percentages, right? We use the proportion, which means we have to divide the 7 by 100. Right? So we get $45 times 0.07. Right. I'll make a note here. This is the amount of tax. Right? We pay tax on the $45. And the amount of tax, we just take the amount that we're paying taxes on and then multiply it by however much the tax is worth. We could figure out what 45 times 0.07 is and then add that up with the $45, and that's going to be the cost after tax, right? And that's what we're going to tip on. But for taxes and things like this, right, taxes and tips, it's going to be a good idea to just rework this equation a little bit, right? Because notice that we've got this common $45, right? And so if you want to get right to the total, right, so not the amount of the tax, but the amount after tax, then we can pull out this common $45, factoring, right? So $45 times 1 plus 0.07. And you might use this if you're in the store, right? You're looking at a jacket or something and you want to know how much it is after tax. Then what you would do is you would take this advertised price, let's say it's $45. Maybe it's a shirt, not a jacket, who knows? Times 1.07, right? And that'll get you to the total after tax, right? I think most things, do we pay 12% tax here? I think, right? So usually if I'm in the store and I want to know how much something is after tax, I'll take the price, multiply it by 1.12, right? 12%, and that's the total after tax. Right? So here, 45 times 1.07 is 48.15. Right? So if you don't know that trick already, it'll be very useful when you're in the store and just kind of wanting to know how much something is after tax, right? Instead of figuring out, okay, I have to pay this much in tax and then add it on, it's just a little bit quicker to just do the 1 point, whatever the amount of the tax is. Okay. So knowing that, what's the total after the tip now? So the total after tip we're paying, let's just outline it here, $48.15 plus 15% tip. This is the same sort of equation that we had, right? But now we have this 1 point, whatever percentage we want to tack on there. Tool, I guess. So we say 48.15 times 1.15. Right, we can just jump straight to that to find the total amount. So we get 55.37. So the total amount, so therefore the total amount spent after tax and tip is $55.37. We'll see this trick again, right? Or if we want to add some percentage of something to it right away using this 1 point, whatever trick. So that'll come up again. How about, oh, any questions about that one before we do the next example? Oh. We can manipulate this the other way. If we have something like this, so example 53. A local pub has offered a $10 dinner, which includes 9% tax and a 15% tip, okay, after tax. What is the cost of the dinner to the pub, right? So now we're working backwards from where we were before, right? So we know the total cost is $10, right? But from that, we have to take a 15% tip and we have to take out 9% in taxes, right? And then we're wondering, how much is that core amount that they're paying? So we've got a total cost of $10. Including 9% tax. Oops. And 15% tip. After tax. Okay. If we recognize that we're just doing what we just did, but in reverse, right, it makes it a lot easier, because what we're saying is that the final product is 10, right? And so something times the tip, right? Because we have to work backwards, right? We have to undo the tip first, and then we can undo the tax. So something times the tip equals 10. So we know that 10 is, let's say, P times 1.15, right? I'll just make a note here. Where P is the price after tax, and 1.15 takes care of the tip, right? Now we can solve for P, right? The price after tax. So P is 10 divided by 1.15. I did a switcheroo here without even really thinking about it, because as always, I like to have what I'm solving for on the left-hand side, right? And so I just kind of move this over here, move this over here. I switch those around, and then I divided both sides by 1.15 in one whoop, whoop, slash. Okay. So we get P, the price after tax, is 8.696. And if you want, we can round this to 2 decimal places if we want to. I'm just going to leave it. I'm not too picky at this point. So this is the price after tax. Right. Before the tip, so we undid the tip. We undid the 15% tip. And so now we're going to do the same thing to undo the tax. Right. And so 8.696 is, let's call it C. And I'll say C is the cost of the meal. Times 1.09. That 1.09, that's the tax that we're trying to undo. So again, C is 8.696 over 1.09. So C is $7.98. Right, so the cost to the restaurant, right, really what they're saying is, we'll sell you this meal for $7.98, but we've already added on the taxes and the tip to make it look better for you. But then you have to pay $10. Right? So these are the same. Right? And being able to add tax or tip and subtract it, right? We kind of have to be fluent in that. Okay. So the cost to the restaurant is $7.98 per meal. Okay. Any questions? So what I want you to do, and really make sure that you get it, is do all the, at least all of the self-test questions on page 37. So section 1.7 is the self-test section. So do the self-test, which is section 1.7, to make sure everything we've learned in chapter 1 makes sense. To make sure everything we've learned in chapter 1 makes sense. So it's not due, you don't have to hand it in or anything, but just make sure that you're staying on top of these things, right? I understand that might be easy for you, and that's good, but just go through and do them quickly, right? Then that's great, it won't take you very long, right? But just make sure that you do them. And then we'll start chapter 2 on Wednesday. So we'll end early. Feeling silly, I should have brought more stuff, but yeah, oh well. ending early doesn't hurt. See you guys on Wednesday. I'll be here if you have any questions or you want to work through stuff.